Hi, in this video, we want to take a look at smoothing time series. All right, so what we're going to do, we're going to take our time series and I want to get I want to use like averaging to get an idea of what's going on as time goes by in, in my time series. Now, if I take an average over the entire time set, then what will end up happening is I have just one horizontal line, and that will be informative, but I want something a little bit more nuanced to individual moments in time. And so we're going to use smoothing. Now, there's several different ways that we're going to explore in this video. First one is convolutions and moving averages, then kernel smoothing, then polynomial trends, lowest curves, cubic splines, and then using another time series to get a deeper understanding into what's going on with the time series I'm interested in. So if I have two time series, one that I'm interested in as a target variable, the other one is the predictor variable, we can look at it that way, then I could use our last technique, our last example method to gain insight into my target time series. All right, so the first one we're going to talk about is the moving average smoother. And we can modify the coefficients on this slightly and have a general convolution, but most often we'll be doing a moving average. All right, so moving averages and just smooth time series in general are good for detecting long-term trends and seasonal components. All right, so for a moving average, what we're going to do, we're going to take a subset of time, and we're going to just take the average. Very simple. Now, a symmetric moving average is where if I'm interested in a point right here, then the weights to the left and to the right will have equal amounts. So I'll have an equal weighted average to the left and to the right, and as I move out, it will be even like that. All right. So one thing to remember is that in a moving average, we're going to have our coefficients that we use are going to sum up to 1. They're all greater than or equal to 0. And symmetric means we have equal weights when I go left and right. All right, so let's go ahead and run through an example. This is from the textbook. And what we're going to do, we're going to say that for plus or minus, 0, plus or minus 1, plus or minus 2, all the way up plus or minus 5 months, we'll go 1 over 12, and then plus or minus 6 months, we'll go 1 over 24 for the weights. And this will be a weighted average over the entire year. Now, why would we be going over the entire year? Well, what that will do nicely for us is that it will remove the seasonal component aspect if I average over the entire year. So if I had my data in days instead of months, I could do 365 different weights. All right, so here is the SOI dataset from the ASTSA package. And we're going to use a forward and a backwards convolution / moving average to smooth the entire time series. And so here I'm going through and I've got my weights. You'll notice I've got a 1 and I've got 0.5. So for 11 of them, I have a 1, and then half as much weight on the two tails. All right, and then after I set that up, so this is, I'm saying it proportionately how large are each of the weights, and then I rescale by dividing by the sum. So now it becomes the weights of a weighted average. So now all I got to do is just set up the weights like this, and we're using the filter function for this. And the filter function, it doesn't have to be average weights. It could be something more exotic, like maybe I'm in a situation where I want to have subtraction for some steps, addition for others, some mixture of what's going on, then the filter function will accept that nicely. All right, so now let's go ahead and plot it and take a look at what's going on. All right, so the blue is our original time series, and then the red line is the smoothed out version. And so it's easier to see what's going on as a trend when I look at the smooth version. Now, when I look at this, I'll notice that there's still a little bit of bumpiness. It's not completely smooth, could be smoothed out a little bit more. And so what we're going to do, let's see if we could smooth this out a little bit with using another technique. Oh, before we get to that, let's go ahead and visualize the weights. And the author chose to do this in this manner, that here, these are all the ones that correspond to 1 over 12. Here, there'll be 1 over 24, 1 over 24 as the weights, and then 0 for all other portions of the time series. And so this makes more sense if you're looking at this from like a convolution point of view, where we have a window of weights passing along in time, and then we're doing our computation, and that's a very convolution point of view to look at it. All right, so that last time series, the smooth plot was a little bit choppy, and it had a little bit of bumps in there that we'd like to see smooth out. Let's see if we can work out something a little bit nicer for our purpose. So let's go ahead and try kernel smoothing. All right, so kernel smoothing, this is very similar to density estimation when I have my data. What we're going to do, we're going to take a kernel function, and we're going to use that function to define the weights that we use in setting up our smooth curve. All right, so what we're going to do is we're going to determine weights using a kernel function. And we have to, at this point, we haven't chosen our kernel yet, but the kernel determines the weights. I'm going to multiply my time series values. And then as I pass along time, I'm going to get each of the time points for the smooth value. Now, how do we determine the weights? Well, I'm going to take my kernel function, and I'm going to divide out so that I can see that I'm going to have the sum of all the weights equals 1 for each individual point in time. Now notice I have to redo this calculation for every point of time that I want to have a smooth value. So if I was to do this by hand, this would take a long time. So K is the kernel function that we choose. Now, probably the most common kernel function out there in statistics to be used is the normal kernel, the bell curve, standard normal. And so here, I just set up that K is equal to the bell curve. And you'll notice that inside here, I have a location scale transform on the variable that's going inside there. And that's how we control our center and our spread. And so to do this, in R, we're going to use the K-smooth function. This is a base R function. And the larger that bandwidth parameter, the smoother the model is going to be. Now, when I make a choice on bandwidth, if I go super, super large, it's going to be nearly a flat curve, or it's going to be so smooth that it's not going to capture the nuances I'm looking for. If it's a super, super small bandwidth, what will end up happening is that it's going to be too choppy, too sensitive to individual values. And so we want to find somewhere in between. Right, so the default setting in R is that kernels are scaled to the quartiles from the probability densities are plus or minus a fourth times the bandwidth. And the same bandwidth with different kernels can give us different smoothness in our models. So as I explore different possibilities, one thing I have to decide what my kernel will be. I have to decide what my bandwidth is going to be. And if you don't know, I would start with the normal Gaussian curve as your kernel to start out initially, and then explore other kernels until you get something you like. And for standard normal, the quartiles are plus or minus 0.674. All right, so now let's go ahead and plot this, and so that this way we can see what's going on. And to plot this once again, I'm going to use the time series plot function from ASTSA, and then I'm going to put my smooth line on top of it. And so here is my smooth line using the K-smooth function. And we're using normal, kernel, and a bandwidth of 1. And so this is a little bit smoother. All right. And so we can see the trends of what's going on from year to year. And now let's just to see the difference between the weighted average, let's go ahead and visualize the Gaussian curve. So something to notice is that it's not flat like it was with the moving average that we did previously. And the moving average, once it got out to a certain point, it was all zeros. Technically speaking, when I use the Gaussian curve, it's never going to be equal to zero. Even the farthest out point away from the time that I'm interested in will have a little bit of influence on the smoothing of my curve. All right, the next one we want to talk about is lowest curves. All right, so another way to smooth our time series plot is to do nearest neighbor regression. So this is 100% correct, but a way to think about this is to take the k nearest points and then run regression. And then from regression, off of the nearest points, I get a modeled value of the point time that I'm interested in. That is our smooth value. By taking in multiple data points to estimate the one point that we're interested in, I get a smoother curve because it's less sensitive to fluctuations in the data. All right, so lowest is a very common method for smoothing, but it's rather complex. The basic idea is think of it as nearest neighbor regression, not 100% correct, but that's a good way to think about it. All right, and so in most implementations, there's going to be a weighting scheme where the time series values closer to the time that I'm interested in are going to have more weight than the ones that are farther away. And then we're going to be using a robust regression technique off of that. All right, so the figure that I'm about to show, use 5% of the data for any particular point that we're interested in to do the plot. So the negative trend in the time series would indicate that the long-term warming of the Pacific Ocean. So to investigate this, the author used lowest with a smoothing span of 2/3. Now, something about the different smoothing techniques is that you can't compare parameter to parameter across different techniques or different kernels for that matter. You just have to kind of look and see and play around with what is going to work out. So here we are using, we're going to plot the time series with a polynomial trend of order 1 and then add a lowest curve. All right, so the blue is our time series, and then we have polynomial trend curve of degree 1. You can see it's very smooth. Then we have our lowest, and we can see like the overall trend very well, very nicely. All right, the next one is smoothing splines. All right, I had a coworker who absolutely loved splines. And so for any modeling, he would jump on board immediately if I use splines. So the point of that story, the reason why I'm pointing that out is that I would use splines not because it was the best model possible, but because I had buy-in. And when I got his buy-in on a project, then largely other coworkers, other members of the team would also buy into what I'm doing. Remember that when we're doing statistics, when we're doing data science, our goal is to convince somebody of something. And so what I want to do, I want to always choose my technique that will deliver the final result that I want, and that is to have acceptance of my recommendations, acceptance of my models, acceptance of my outputs. All right, so what we can do, we can smooth the data with a polynomial regression in terms of time. All right, so what we're going to do, we're going to do cubic polynomials, so degree 3 polynomials on time. So our model is going to be that our central tendency, our modeled central tendency, is going to be a degree 3 polynomial on time. And then we're going to take that plus our noise term. All right. And so, and we're going to fit this polynomial using ordinary least squares. Now, how does this become a spline? Is that we're actually going to chop up our interval, and the cut points of our intervals are going to be called knots. And what we're going to do, we're going to do a cubic spline on each of these sub intervals. And so that's how we get our cubic splines. All right, so a related method to this is that something that we can do is that we can consider the fact that we can overfit with our model, and we don't want to overfit, of course, but we also don't want to underfit. We want to find that balance. So one way to find that balance is to try to minimize this term here. So this is our observed data minus the modeled values squared, added up. So this addresses the accuracy of the model. How well does the model fit my data? Now, this summation is not going to take into consideration an overfit model. All right, so basically an overfit model would be absolutely perfect by that measurement right there, because it would be as small as possible. Well, I don't want to overfit. So what we're going to do, I'm going to add on a penalty term to help prevent myself from overfitting. And what we're going to do, we're going to take a parameter, a smoothness parameter, and then we're going to multiply by the integral of the second derivative of our polynomial, square that, and then integrate over the entire interval session. All right, and so this integration is actually going to be over all of our sub-intervals. All right, so what will happen is if I have a very, very large lambda, then the goal would be to have a very, very, very small integral to make sure that the overall term is small. So I want this overall term to be small. If lambda is big, then it's more important to have this integral small, which means I'm going to it's going to be more important to have a smoother curve than it is to actually fit my data. If lambda is small, let's say, think of it as just zero. Let's say that lambda was just absolutely zero. If it's very, very small, then the only thing that's important is the accuracy. And there I'm going to have a very choppy, not smooth at all model. And so there, it's going to be kind of like a balancing act. How, I want a lambda that gives me smooth enough that it's I can understand what's going on. It's easy to look at, easy to interpret, but I don't want to sacrifice my accuracy too much. And so it's a balancing act. So small lambda places more importance on model fit. Larger lambda places more importance on fitting a smoother model. And the idea here is that if I think of the second derivative, well, in physics that corresponds to acceleration, deceleration. And if we were to use our modeled smooth curve to represent the acceleration, deceleration of a car going down the road, well, here, if lambda is sorry, let me back up, a larger value, I want this, when it's equal to zero, it's going to be a constant velocity, just no acceleration, no deceleration. If I had a bobblehead on my dashboard, the bobblehead would just sit still. A choppy ride where they're gunning it, hitting the brakes, gunning it, hitting the brakes, gunning it, hitting the brakes. You're getting whiplash from riding with this guy. This would be a more fluctuating function. All right, so if lambda is equal to zero, we don't care about the choppiness of the ride, which leads to really just our model value being the individual data points, which will not be smooth. It'll be very, very choppy. If lambda is large, we insist on very, very little acceleration or deceleration. And so we would have a constant term for our average or our model value. And so SPAR, smoothing parameter, is the parameter in the function to control this in R. Use smoothing splines help documentation to check out and read this. I recommend that you read this before you start using this method. And so let's go ahead and look at two different models, one with a smoothing parameter of 0.5 and one with a smoothing parameter of 1. And so here we can see that this one, we have the red is much smoother than the blue. All right, so now another thing we can do is that we can do smoothing on a time series using another time series, as long as we have them for the same time points. All right, so we're going to look at an example that uses mortality and temperature. And so what we're going to do, we're going to make a scatter plot over mortality and temperature and fit a lowest curve. And something that we're going to see in the plot is that mortality increases at extreme temperatures, but in an asymmetric manner. Mortality is higher at colder temperatures than at hotter temperatures. And the minimum mortality rate seems to be around 83 degrees Fahrenheit. And so here I'm going to load my data. Here's my time series plot. You notice I've got both time series in here. And then I'm going to fit a lowest curve. And I'm going to put that on top of the plot I just created. And so here we can see that curve, and it looks like the lowest mortality is around 83 degrees, and the highest mortality is at the far left and far right, extreme temperatures. So extreme cold looks like it corresponds stronger with high mortality rate than hotter temperatures. All right, well, that's all I've got for you. Take care and goodbye.